Okay, hello everybody. Thank you for coming today. Today is our sixth lecture. We're talking today about linear classification, so we're still sticking with classification problems. And I'm going to show you two different very popular methods of performing linear classification, and I will show you how they are derived and how they work. So we will start with the formulation of our problem. So we have two classes that we label, whichever way we like, and those two classes, our data that we have, will be somehow distributed in the space. And we now want to find a line that separates the two. A linear classification boundary, which will be in general a hyperplane, which will separate the space into two half spaces, right? And what lies in one of the half spaces is classified as the positive, or say the x or the 1, and one is classified as the other half space. Everything that lies in the other half space is classified as the negative, that is the circle, or the 0, or the -1. Now, the question is, of course, how can we efficiently and meaningfully find such a line? So, of course, if the data is scattered in 2D like this, I can simply draw it, but in general, we have the problem of finding such a line. And when we think back to the first lecture, the first thing that we find is that the model we have is of the form omega transpose x smaller or equal than some threshold b. And where it is smaller or equal, we classify as negative. Where it is greater than b, we classify as a positive. So there are a few ways of finding the best or the most suitable separating hyperplane. And we have to answer the question how to efficiently and meaningfully choose the two parameters of the model. Now, we could, for example, say we want to minimize the number of misclassifications. So if we had the scenario that there was a circle here and an x here, we might find a different hyperplane. Actually, we could by tilting it a bit, where we have lesser number of examples which are misclassified. However, doing this, minimizing the number of misclassified examples, is an NP-hard problem. NP hard is in some sense a measure of the difficulty, computational difficulty of a problem. And if it is NP hard usually, that means that we cannot meaningfully use it in practice because it is too slow. It takes too much effort. Also, if we want to have probabilistic interpretation, we're facing the problem that if we just look at the hyperplane here, we can see that what we get are real numbers. However, the probability is in the range 0 to 1, so we have to somehow translate the linear expression into a probability. One solution, the first classifier that we're looking at today, is the so-called logistic regression. Where does the name come from? There's a function, sigmoidal function, that is also called the logistic function. And what we're doing is we're kind of trying to fit this logistic function in to our data. And this is why we call it a logistic regression problem. But it has not really anything to do with logistics. And what we do is we look at the odds of a sample being in a class instead of the probability itself. So more specifically, we look at the logarithm of the odds. So the odds are the quotient of the two probabilities. That means that you can, because we're just having two classes, that means we can write it in the form of just one single probability and of 1 minus, because being in the class 0 is the probability of being in the class 0 is the probability, is 1 minus the probability of being in class 1. And now the model is this, the logarithm of the odds is modeled by a linear function. Now, how did we get rid of B? Quite simple. If the odds are in favor of the one class, if the odds are in favor of class 1, we choose the class 1. If they aren't, we choose class 0. So basically, if this is greater or equal than 0, we choose class 1. If it is smaller than 0, we choose class 0. So we can now also, if we had a bias, so we could have said we want to add some constant c here as well. What we would do is we could just extend the data by one dimension and add a constant column of zeros, or the last component of each data point could be a 1, and then finding the coefficient for this one component, constant one component, would be the same thing as finding the bias, finding this shift, finding the c that we wanted to add in the first place. So here we have that trick written down. Okay. Also, we note that the odds will always be a positive number, a strictly positive number in our model here. So the logarithm will give you here a real number now. Let's write that down. And by the way, actually, this is independent until now of our specific model, right? We just derived something that holds true for all classification tasks here. In all binary classification tasks, that is. So we can now derive our maximum likelihood estimation the same way we did it for linear regression or for any other model that we have at hand. Okay, so we have logarithm p minus 1 over the probability . So we can do this transformation, and we can also now define the sigmoid function in general of a real number of t as 1 over 1 plus e to the power of minus t. How does that function look like? It has two asymptotes at 1 and 0, or two limits 1 and 0. It's monotonic increasing, and at 0 it will have the value 1/2. So now we want to maximize probability of our model, of our weight vector given the data, and we can do that by the maximum likelihood estimation, doing the trick again with the product, applying the logarithm to the product, and so on, also using Bayes' theorem, stuff like that, and that is then equivalent to minimizing this sum of logarithms. We can rewrite that now. If we know that y is a Boolean number, is our class is either 1 or 0, and now we can pull apart the logarithm, because we know only one of the two expressions will be unequal to 0, right? And write it like that. Okay, now we're pretty much done, because what is now left for us to do is to calculate the derivative. One thing maybe that I should tell you now as well, that you can verify quite easily, is that the derivative of sigma with respect to t is equal to this, so we have some differential equation here that we can exploit. Okay. So now let's calculate the gradient with respect to our weight vector. And we get, again, the sum over all the training samples that we have. And we can rewrite this sum here as a matrix vector product, as usual, almost. So note that each sample influences the gradient with the amount that we're currently wrong. So if you have a current choice for your hyperplane and you have one sample that is classified correctly, what happens is that this term here, this difference, is 0 or almost 0. So if y1 is equal to 1 and we classify our sample as being in the class of 1. So this term, omega transpose x1, would be very high, which means that sigma of omega transpose x1 would be very close to 1, which means that the difference between the two is vanishing, very small. However, if we have one sample where the classification is 1, but the label is 0, then the difference is very big. And the sample is weighted in the gradient with almost a factor of 1. Now, can we set this expression for the gradient? Can we set it to 0 and solve it analytically? It's not that easy, actually. It's not possible with the common operators. However, we can solve the problem with any other method of choice. So we can iteratively solve this system of equations, or we can apply gradient descent and minimize the problem, minimize the objective function, just as we would do with any other problem. And so the way to solve it now would be so to solve it, what we would do is we prove that the objective function we have is convex, and then we can simply apply gradient descent and this way solve the optimization problem. All done? Okay. So as always, we can add priors to that. If we have an idea which models are more likely than others. So because we can just add them, add the prior, add the objective function that we get from the prior to the objective function that we get from the stochastic model. And note that this only requires a change, then the addition of the gradient that we get from the prior. So this is literally everything that changes here. Okay. So another version, another way, different solution to the question, how can we fit the line, how can we separate the two data sets by the two classes by a line, is the so-called support vector machine. Or in short, SVM. Now, the idea behind that is if we have our two classes, and maybe they are linearly separable, that means we can find a line that goes through them, that separates the two classes, then what we could do to choose our line is to say we want the line that maximizes the distance between the two classes, or in other words, where the distance of each class from the separating hyperplane from the decision boundary is as big as possible. And that is what we call the margin. So to derive the support vector machine, we want to maximize the margin of the model, and that, we hope, makes our model more robust, because the decision boundary is as far away as possible from the data points that we already have. So I drew a new data set because it will make it a little bit easier for me to draw in it. So how would the optimal margin, the maximum margin classifier look like? Let's draw that in. So geometrically, we can see that this line here, or the 3 points which lie closest, will somehow define that, right? And the line, the separating line, will be parallel to those two hyperplanes here. And it will be the one which bisects the space between them. So this here is our margin, or 1/2 of our margin, M. And for the sake of for the sake of an easy computation, we can say here it holds true omega transpose x plus some threshold b is equal to 1 for the circles over here. It must be -1, so we're the same way away from the neutral part where it is 0. Okay, so now let's see, can we derive that? How can we derive a formula or some problem from which we can generate the optimal margin hyperplane? You know, for the crosses, it holds that omega transpose x plus b is equal to -1. And we know if we go half the margin in the direction of omega, so omega will be the normal plane here to our hyperplane, then we will get here and it will be 0. Or if we go the whole margin, m long in the direction of omega, then we will have that expression be equal to 1. And now we can rearrange that here, because what we have is omega transpose x plus omega transpose times m times omega divided by the length of omega plus b is equal to 1. And omega transpose x plus b, you already know what that is. That is -1. And we get m times the length of omega is equal to 2. So if you want to maximize m, we would need to maximize this term, or equivalently, minimize the length of omega. And what I should emphasize is, so x here had to be a data point that is on the margin here. So we could not have taken an x from here because there we don't know what omega transpose x plus b would be. But if it's 1 over here on this line, then we know that it has to be minus 1. And from that, we can now derive a constrained optimization problem. Because instead of minimizing just the length, we can also minimize the square of the length. And we want to demand that each cross has a negative value if you evaluate this linear function here, and each circle is supposed to have a positive value. And if we now say with the y and minus 1 or 1, so for crosses it's minus 1 and for the circles it's 1, we can write that constraint as saying y I yi times omega transpose xi plus b has to be greater or equal than 1. So there are a few questions left now. So first of all, note that with that sign here, basically multiplying with the label is the same thing as changing the sign. So when we have a data point that is a circle, what it reads here is omega transpose xi plus b has to be greater or equal than 1. Okay. If we had minus 1 here, then we would have, or do we have a sign? Error in the sign here? Let me check. No, it's all fine. Okay, sorry for the confusion. If we have a minus 1 here, we could multiply the whole thing with minus 1, right? So we would get omega transpose xi plus b is smaller or equal than minus 1, which is exactly what we wanted. Why can't we simply say we want to have that it is at least 1 or a maximum minus 1? We can do that because as long as it is separable, we can find some tiny margin in between, and then we can just multiply both omega and b by a factor until we get a separation of 1 here in terms of the numerical value. And we still have a problem. Because we assumed that the data is linearly separable to do this. And if it is not separable, then what we could do is we change the constraints with so-called slack variables. That we have for each data point. And we say now our same expression can be artificially increased with the epsilon I. However, if we do that, it comes at a cost. We penalize that here. So, why can we solve that? Can we solve that problem here? It turns out we can, because everything here that we have, every function that we have is convex. So our objective function is the sum of two convex functions, so omega transpose omega. And the sum of the epsilon I is convex. Epsilon I has to be greater or equal than 0. And also our constraints are just linear constraints. So we have linear constraints are convex, if you think back to our second lecture. So we have a completely convex optimization problem here that we would need to solve. And that, of course, begs the question, can we derive a dual problem here, maybe, for our support vector machine? Let's look at that. So first, we would write down our Lagrange function that we have. So I'm deriving the problem for the linear separable version because it's a little less cumbersome and maybe easier to understand for you. And for the sake of computation, we can write a factor of 1/2 here. Which obviously will not change the minimal point, right? So we have rewritten the constraint functions that we have from the inequality to the form where we can say g of x is smaller or equal than 0. And let's see if we can now minimize that with respect to our primal variables omega and b. And we get those two derivatives here, and we want to set them both to 0. So from here we will get an expression for omega, and here we get another equation. So first of all, we note that it follows omega is equal to x times this, and that implies that omega is in the span of x, in the span of our data points, I'm sorry. Which is quite an interesting thing, right? So we just derived that the weight vector that we're looking for is actually a linear combination of the data points we already have. That might be something of interest here. And indeed, it turns out that many problems, linear problems, or problems linear in nature that we consider in machine learning have this property that the desired solution is actually in the span of the data points that we have, and that can come in handy in some situations, as we will soon see in the future. So that means we can write the dual Lagrange function in terms of alpha, and we get -1/2 times alpha transpose diagonal matrix of our y times x transpose times x times diagonal matrix of the y times alpha plus the sum of the alpha. And we can call this term x times the diagonal matrix of y. We can call it x tilde, and we can already see that we again have something of a quadratic optimization problem, where we have here symmetric positive definite matrix, symmetric positive semi-definite maybe, and here's a minus, so it will be an concave function. However, because we maximize, we're good, everything works. It's like minimizing, maximizing this term will be like minimizing minus this term here. So we have still a convex problem, just as we expected, and we now have to maximize. L hat of alpha subject to alpha transpose y is equal to 0, and alpha has to be greater or equal than 0. So this we get from our demand here that we're at the optimal solution. So we got two equations here. The first one we used to derive an expression for omega, and the second one we must not forget about that here. And here it comes back as an additional constraint. So we again have a convex problem here. So our problem becomes minimizing minus the dual Lagrangian function subject to two constraints. First, alpha transpose y is equal to 0, and alpha has to be greater or equal than 0. And if you now remember our results from our optimization lecture, we know that there's complementary slackness. We know that the multiplier from a constraint is can only be non-negative if the constraint is active, if we actually run into the wall. So either one of them will always be 0. Either the constraint is 0, then it's active, then our multiplier can be non-zero. Or if the constraint is not active, then we know the multiplier must be 0. So we know that the sum of multiplier times constraint function is 0. And that gives us, at the optimum at least, and that tells us that if alpha I is actually greater than 0, then omega transpose x plus b must be plus minus 1. So if the multiplier is non-zero, then we know the training sample in question is on the margin. And this is where the support vector machine derives its name from, because the vectors, the data points that have a non-zero dual multiplier, only they contribute actually to the margin, to the hyperplane, to the definition of the hyperplane. So the hyperplane is, in some sense, supported or defined by our support vectors, by our data points of non-zero dual multiplier. Yeah, and if in case that wasn't clear, so just to emphasize that, we have one constraint for each data point. Therefore, we have one multiplier for each data point. And now we basically have rephrased the problem in terms of our data points. The dual problem is a representation of the problem, of the primal problem, in terms of data points, and not anymore in terms of the weight vector. So only the data points that are actually on the margin define the support vector machine. And that is very interesting, right? Because it means that for solving the classification problem, you actually don't need most of the data. You only need the data that is close to the decision boundary, which is also something, right, that you might intuitively think that what is important is not the data points that are right in the middle of one class, but the ones that are on the outside, and especially the ones on the outside where that are close to data points of the other class. And that reduces the size. It reduces the size of our data points effectively from the number of data points we have down to just the number of support vectors that we have. So also when you look at something theoretically, it is very interesting what we have just figured out here, right? You can think of a classification problem purely in terms of the support vectors that define it. That also means that you only need to keep track of support vectors. If you have a way to figure out what data point is a support vector or what might be a support vector and which one will not be, then you only have to keep them in memory and you can let go of all the rest. And that is a very, very helpful finding when you want to apply such methods on in the context of large data sets. So we call a data point xi, where the Lagrange multiplier is unequal to 0, a support vector. So if we actually want to do classification now, if you want to calculate the label, we can either use the primal formulation by using the weight vector omega explicitly, or we can use the relationship that we derived to express the weight vector in terms of data points and write it in terms of data points. And if you want to evaluate this expression, what we do is we trade the scalar product of the weight vector with x. We trade it with a bunch of scalar products of data points with a new data point. And that is, as it will turn out, quite a big difference. That can make a very big difference, especially if it might be very hard to compute the scalar product of arbitrary two vectors in some space, but it can be easier to calculate the scalar product of very specific vectors in the high-dimensional space. And if that is the case, especially if we know that the data that we have are those special kind of vectors, then this might be way easier than this, even though in terms of the number of scalar products, we have just one scalar product here, and here, in the worst case, it scales with the number of data points that we have, which is a lot, which can be a lot. So in summary, logistic regression and the support vector machine are for binary classification problems. We can extend it to more classes, but basically what we would do what we have to do then is that we have to reduce the multi-class problem into a bunch of binary classification problems. Both have convex optimization problems, which means that the results that we get are reproducible between two people who have the same data set, and the optimization, the training process can be done very quickly, can be done computationally efficiently. The support vector machine is robust due to the choice of the maximal margin in its derivation, and also something that we cannot go into too deep in the lecture. There's a tiny homework regarding that. You can derive bounds on the performance of support vector machine. So there are guarantees that a support vector machine, given the data that you already have and things like that, will not perform worse than a given bound. And that is quite a strong thing, right? So you know, you have a guarantee about the generalization ability of your support vector machine. However, how usable those bounds are in practice is a different question. And both are simple models. And the decision boundary is a hyperplane. So that might be a benefit, or it might be a disadvantage. It depends on the data that you have. Okay, so much for the two linear classifiers with the support vector machine and the logistic regression. note that there's an abundance of other linear classifiers as well. Things like the perceptron algorithm, which can be considered the first idea of a neural network, or many different variations thereof, and they are different flavors of the same thing. Each of them has a different motivation. So the logistic regression had its motivation in a statistical model that we derived. The support vector machine had its motivation in choosing the maximum margin for our classifier, and other classifiers basically just implement a different way of choosing your best decision boundary. Okay, so much for the two. Thank you very much, and see you next time.